In the last lecture, we were discussing about the extended objects, and in particular we are now trying to study the how to analyze problems with rotational motion. And in the last lecture, we introduced this concept of center of mass, and we took several examples of center of given an extended object with a certain mass distribution, then where at the location of the center of mass and how to find that. Today we are going to take a example. So, this is an interesting example in which so this is more kind of probably realistic example. So, today we are going to discuss how to find center of mass of a composite object. So, composite objects I am going to so this is something where the object has some shape which is not a regular shape. So, in the last class we discussed simple shapes like a straight line or a circle or a disc or a square or a triangle and so on. But often we come across objects where whose center of mass we want to find, but we cannot describe the objects with such simple shape. However, if we are lucky, we can still describe the shape of the object as a combination of simple shapes, and this is what I mean by composite objects. So, here is an example. So, the shaded area, the blue shaded region represents a mass distribution. So, this is where the mass and is located, and so this is the shape of the object. And we are interested to identify the location of the center of mass, that is a problem. Now, as we know, we can start with the basic definition of center of mass and find just by first principle calculation, which is most general and most of the time the only practical way. But here we can notice the following, that the shape of the object we can sort of describe in the following way. So, we have a quarter of a circle, and then we have a triangle inside this circle. So, now if we scoop out this triangular area, triangular portion from the circle, then we get the given mass distribution. So, in this case we can follow this strategy that, so it is easy to find the center of mass of a triangle and the center of mass of a quarter of a circle. So, then our strategy will be find the center of mass of the triangle. So, let us say the triangle has center of mass somewhere here, and let us say the full circle will have center of mass at in this location. This is the circle and this is the triangle, and this particular shape, let's say the center of mass is here. So, then if we replace this triangle by a point mass, so this is x, this is y, this is x, this is y. So, this is the center of mass of the triangle, and this is the center of mass which is unknown of the shaded region, and then this, if we combine these two center of mass, we know we should. So, now you think of this triangle as a single point and the shaded region as a single point located at the center of mass. Now, if we combine them, then we know that we can define the center of mass of this combination, and we know that this must coincide with the center of mass of the full quarter of the circle, because if we add the triangle and the shaded region, that makes the quarter of a circle. So, this is going to be our strategy. Now, I am going to work out this problem in some detail into sort of show you the algebra in detail. There are several interesting aspects about this algebra. So, let us start doing this calculation. So, first I am going to look at the center of mass of the quarter of a circle. So, we have this circle 1/4 of a circle. So, according to the picture it has a radius a. Now, if we write down the definition, if you recall the definition, consider a particular mass element shown in this square block. Let us say, so this is our origin, O is our origin and these are the coordinate axes, and then assume that this mass element is located in at the point x y, which is inside this circle. So, then our definition, and then let us say the sigma is the density of the area density, that is mass per unit area, and I am going to assume that this is the mass distribution is uniform. So, this sigma is a constant. So, then we can write by definition that the center of mass of, if I take the location of x, its x coordinate is x, and let us say its mass contribution is dm. Then if we add over all such elements and then divided by the total mass, that will give us the x coordinate of the center of mass, and similarly the y coordinate of the center of mass. So, our first task is to calculate these integrals. Now, for a circle, these integrals, the natural coordinate system will be 2-dimensional polar coordinate system, but since we have not introduced them in this course. So, we are going to use Cartesian coordinate and do this calculation. So, let us first calculate the total mass. So, we know that the total mass will be, let us say if the total mass is m of the quarter of a circle, then m must be the density times the area of the circle. So, area of the circle is pi, the radius, and this is quarter of a circle. So, the full circle divided by 4. So, this is, we know that the answer. So, we know the answer. So, now we are going to do this integral to get the answer. So, this will give us some practice in the calculation. So, this integral can be written as so dx dy. So, this is going to be a 2-dimensional integral or an area integral. So, here, so I am going to write 2 variable integration variable for that. Now, let us think about the limits of the integral. So, for the x, the limits is easy, it goes from 0 to a as in the picture. So, x equal to 0 to a. Now, for the y goes from the x axis to the perimeter of the circle. So, the perimeter of the, so the circle is given by the equation of the circle, which is x square plus y square equal to y square. So, y is equal to a square minus x square. So, the y goes from 0 to a square minus x square, and since the limit of y depends on x. So, we have to do the y integration first, we cannot switch the x and y order of the integral. So, if I do the, so I can take the sigma outside the integral. So, I can write as and the x goes from 0 to a, and if I do this integral, I end up with a 1-dimensional integration now only in x. Now, to do this integral, so let us recall that let us change the variable, that let us call x equal to a sin theta, and then dx is equal to a cos theta d theta. So, this a square minus x square is equal to a cos theta, and when x equal to 0, that means that sin theta is 0, that means theta is 0, and x equal to 1, that means sin theta is x equal to a, then that means sin theta is x by a, which is 1, which means theta is equal to pi by 2. So, in our new variable, this is going to be So, so we have dx is a cos theta d theta times a cos theta 0 to pi by 2. So, this is going to be sigma times, so I can take a square outside, we have a cos square theta d theta 0 to pi by 2. Now, this cos square theta d theta 0 to pi by 2. So, this is equal to sigma a square 0 to pi by 2 half 1 plus cos 2 theta d theta. So, you can check that the second term will, the integration over cos 2 theta term will give you 0 from 0 when the limit is 0 to pi by 2, and the first term will give you contribution of pi by 2. So, we get sigma a square times half times pi by 2, and this you can compare with this expression that they are matching. So, we need to come to our main focus, which is to calculate these first integration. So, in the first integration there is a new integral in the numerator, which is going to be x times the mass. Again x goes from 0 to a. Now, we again this is going to be a two dimensional integration, because the mass is given by this expression. So, this is, and so this is a two dimensional integration. So, note that this integral is very similar to the earlier integral, except the factor of x present here. So, I am going to write it as, take sigma out. So, again we have to do the x y integration first, and the y integration we know will give us this factor of s square minus x square. So, now it is a one dimensional integral in x. So, again we play the same trick. So, we use this variable change. So, then if we use x equal to a sin theta, then we get, so dx is going to be a cos theta d theta, and x is a sin theta, and square root of x square minus x square is a cos theta. Now, this goes from 0 to, so this is x equal to 0 to pi by 2, this is theta equal to 0 to pi by 2. So, now if I do the simplification, we get sigma times a cube. So, note a cube has a dimension of length to the power 3, and this makes sense because we have x and a dx and dy. So, this will have, so this object, this integral will have a and hence you get this dimension of a length to the power 3. So, so far we are consistent. So, the rest of the integral variables are, so you have a cos square theta sin theta d theta. Now, sin theta d theta is nothing but d of cos theta. So, we can write it as, so this is still theta equal to 0 to pi by 2, but now we take cos theta as the variable, then this is going to give us a something like cos square theta d cos theta, and cos theta varies from 1 to 0, because when theta equal to 0 cos theta is 1, and when theta equal to pi by 2 cos theta is 0. So, this gives us like a 1 by 1/3, sorry, there is a minus sign here. So, there should be a minus sign here, and then we can absorb the minus sign by reversing the limit of the integral. So, this is going to give us sigma a cube times 1 by 3. So, now we have calculated the numerator and denominator. So, then our x c m is going to be sigma times a cube times 1 by 3 divided by sigma times pi a square divided by 4. Now, if we do the simplification, we get sigma cancels. So, this is the beauty that even though we introduced a unknown variable sigma, but we are going to see that as long as our mass distribution is uniform and the density is constant, the density can be will get cancelled. So, this a cube by a square will give us a, and the other factors will give us 4 a by 3 pi. So, you can do the same way, you can calculate the y coordinate of the integral, and so I leave it to you as an exercise to show that the y will has the same value. So, this is also 4 a by 3 pi. So, that give us the location of the CM of the circle, which is at 4 a by 3 pi comma 4 a by 3 pi. Now, our next step is to find the location of the triangle. So, the location of the triangle, location of the center of mass of the triangle. Now, the center of mass of the triangle is located at a point called the centroid of the triangle. So, this this is a standard result of geometry. So, we have a triangle which is right circular triangle. So, let us this is our origin. So, this is 0 0, and this point let us call that O, this let us call that B, and this point A. So, this is O, A and B, and from the picture you can see that the coordinates of O, A and B are the following. Now, let us show that the center of mass of the triangle will be located at the centroid. So, what is a centroid? Centroid is the point that if you take the middle point of any side of the triangle, and then you connect the opposite vertex to the middle point, and then do it for the another side, and do it for the third side. So, it can be proved that all these points are passing through the same point, they intersect each other precisely at the same point, and this point is called the centroid of the triangle. Now, let us give a physical argument. So, this is a kind of a geometrical proof that you have, I am sure you are familiar with from your high school course. So, let us look at give a physical argument to show that this must be the center of mass. So, since the triangle is uniform the mass density is uniform. So, this let us take this point, this line AD is going to divide the triangle into two pieces. So, on the left piece and the right piece, and by symmetry, because if the mass density is uniform, then it is easy to see by symmetry that these two pieces will have equal mass. That means the center of mass. So, this will give you a kind of a physical understanding of center of mass. So, the center of mass is a point which is kind of balances the. So, we are going to replace an mass distribution of an extended object by a single point. So, intuitively we expect that the mass distribution of that object must be symmetric or balanced in some sense about the center of mass. So, if we follow that line of reasoning, then we can immediately see that the center of mass must lie on the line AD, somewhere on the line along on the AD. Now, we can do the same thing with this line OE. So, the line OE must also divide the triangle into two pieces. Let us call that up piece and the down piece, and again these two pieces must have same mass. So, that means center of mass must also lie on the line OE, which means that the center of mass must be the point of intersection of the line AD and OE, and this is precisely the geometrical definition of the centroid of a triangle. Now, I am going to in the interest of time, I am going to use a identity that the centroid, if the vertices of the of a triangle are located at these 3 points, then the coordinate of the centroid of the triangle is given by this beautiful relation, and this you must have seen in either geometry or coordinate geometry of high school, but we can sort of see it immediately by applying the center of mass definition. So, if G is the center of mass, now if you place 3 equal mass of size m, any size arbitrary mass at the 3 location, then the center of mass of that 3 vertices is going to give will be by definition mx1 plus mx2 plus mx3 divided by 3m, and the m will cancel, and we see that the coordinate of the centroid must be given by this beautiful formula. So, you are going to apply this formula, and in this case the coordinates are given here. So, that means the location of the center of mass of the triangle will be given by 0 plus a by 2 plus 0, which is given by divided by 3. So, this is a by 6, and the y coordinate will be 0 plus 0 plus a divided by 3, which is going to be a by 3. So, this is the center of mass of the triangle. So, now we can replace this. So, now let us say the center of mass of the shaded region is x s and y s, and x s and y s are unknown. So, what our strategy is going to be that we replace the triangle by its center of mass. Now, so this is point G, which is a by 6 times a by 3, and it has some mass m, which is equal to the mass of the triangle. So, how much is the mass of the triangle with the same density? So, that is easy to find. So, this is going to give you this is given by the density times the area of the triangle, which is half into base into height, which is given by sigma by 4 square. And similarly, the let us say, and we are going to put the shaded region. So, the shaded region we do not know where this location, but let us assume this is here. So, this is the position of x s and y s, and this has some mass of the shaded region, and then we are going to replace the triangle as a quarter of the circle as its so this is the circle, center of mass of the circle, and the circle has a, so this is the mass of the triangle if it were present, which is and the mass of the circle we just calculated. So, this is sigma times pi a square by 4. So, then we can see that the mass of the shaded region must be the mass of the circle minus mass of the triangle. So, this is going to be sigma a square by 4 pi minus 1. So, now we have to calculate the center of mass location. So, again, so we are going to use this definition that, so this is the center of mass of the triangle and this is the center of mass of the shaded region, this is the center of mass of the circle. So, the center of mass of the triangle, so m t times, let us write it in a vector notation. So, let us call it r triangle, center of mass of r triangle, plus m shaded region times the position of center of mass of the shaded region must be equal to divided by the total mass of the, which is nothing but that of the circle. This must be equal to the center of mass of the circle. Now, if I look at the x coordinate of this equation, we get mt times x triangle plus ms times x s is going to be mc times xc. So, mc is mt plus ms. So, then our unknown is xs. So, xs is going to be mc times xc minus mt times xt divided by ms. So, our mc we have found that sigma times pi a square. So, let us note down the values. mc is sigma times pi a square by 4, mt is sigma times a square by 4 and ms is sigma a square by 4 into pi minus 1, and we have our xc. So, the xc was the center of mass of the circle. So, this is located at 4a by 3 pi, 4a by 3 pi. So, this is the c, this is a by 6, a by 3, and let us say this is our xs and ys. So, times a by 4a by 3 pi minus mt is sigma a square by 4 times xt is a by 6 divided by sigma times a square by 4 into pi minus 1. So, sigma gets cancelled. So, we have this 4 gets cancelled, the pi gets cancelled. So, we have a by 3 minus, so a cube by 3 minus, on the numerator we have a cube by 3 minus a cube by 24, which is 7 a cube by 24, and the numerator we have a square by 4. So, 7 a cube by 24 divided by a square by 4 is going to be a divided by 7a divided by 6, and we have a factor of pi minus 1 here. So, pi minus 1. So, the answer is 7a by 6 pi minus 1. So, this is the location of the center of mass, x coordinate of the center of mass of the shaded region. So, now I put it as a take home exercise, and you can start from this equation and look at the solve for the y coordinate of the shaded region and show that this is going to be a by pi minus 1. So, to summarize, what we have discussed in the last couple of lectures is that how to find. So, if you take an extended object and if we want to analyze its rotational motion, then sometimes we need to know the center of mass location, which is a representative point, a single point about which the mass distribution is kind of balanced or symmetric, and our goal was to show how to given. So, the type of the problem is the following. So, given the mass distribution, given the object of the shape and given the density of the object, I then use the definition of the center of mass and identify its location. So, this is mainly an exercise in calculating the integrals. So, we gave several known results of simple shapes such as line, rod and circle, ring, etc. And for practical purpose, we also discussed something called composite objects, which are made of combination of these simple shapes, and how to find the what is the strategy to find the center of mass of composite objects. So, in the next lecture, we are going to look at another very basic quantity required to analyze the rotational motion of an extended object. So, this is going to we are going to talk about moment of inertia. Thank you.